Tension-only bracing are of interest to our architect friends in here. Clearly, that is something that they feel is a necessary element just because it's a light structure. And necessity is the mother of invention. So here we are with this research project, SMA device. So we would say that tension-only bracing system is perhaps not the most desirable thing because we anticipate large deformations that perhaps could be locked inside the system, which can be compounded over time when it goes through an earthquake. So we started this research by looking for inspiration from different industries. And we ran into the medical science in place. We also ran into the NASA technology. And we came up with we looked at this shape memory alloy, which was used for quite a few decades, I would say, in these industries. It was perhaps of interest to us because of its super elastic nature, where the original shape can be completely restored. And then we looked further into it, and we figured out that this research was also done in the structural part, and there were applications in the structural industry as well. One of the common example is the one that exists in Washington, where in the Berkeley-PEER we had this shape memory rod that was introduced in the rebar at the Berkeley-PEER. And the other application perhaps is in Europe, where they were used as straps on the slab, and that is to basically close up the cracks as well as compensate for the reinforcement in the slab. And then we were starting to work on this UC Berkeley project, and we thought of perhaps having this as a potential application. And when we started introducing it to John Mitchell was there as the dean of the capital projects, and we showed him this research that we have been doing, he mentioned that maybe you should talk to PEER, because if there is something like this, and if it works, then PEER would definitely know about it. And that's how we came across, and John set up this meeting with Professor Khalid, and we came in and we presented this, and we waited for this, abated breath to talk to Khalid, like what is his response going to be? And that half an hour that we spent talking to Khalid was perhaps the most interesting thing, because we were of the opinion that he is going to kill this research right away, and he came with a complete different background, and he was like, this is what I've been working on. I have a paper on it. Let me send you this. And while we were talking, and here are papers popping over, which we were told to read and come back to it. So thank you for that. And that is when we initiated the conversation of having this PEER shake table test. And really speaking, it was on April 5th. And we had just like about 10 or 11 weeks to really make this happen and have the fabrication done, order the materials, get it in place, install it, and then have the shake table test. It was a mission, and hopefully the mission is accomplished today. We'll wait and watch here. And before we speak a little more for people who want to be familiarized with this particular material, it has the strength of steel, but it can regain its original shape after an elastic deformation. And there is a shape memory behavior which is temperature induced, where it allows for recovering of the shape after the heat is applied. And the other important property is about the super elasticity, where when it's released with it goes into this elastic phase, but without yielding the material, so that it can regain back its normal state, get back to zero if it remains in a particular strain, that's about 5 to 6%. If it goes beyond that, yes, there is there is hardening, which can also be recovered through heat induction. And engineers, we are all interested in the stress versus strain plot, and here it is for you on the left side. The material that we are using is nitinol, nickel, and titanium alloy. And there is a generic diagram of this stress strain curve where we can see that up till 6%, this material will gain its strength, but it can still come back to its original state, in fact, to 0, even if it has gone there. And through the flag shape hysteresis, you can get the energy dissipation. And at higher strains, the material goes into the hardening shape, at which the stresses it can be recoverable with heat induction. So these cables are made up of individual fibers combined into strands. And the strands are woven to create this cable. And through testing, we have observed that the importance of this angle of the cable on the force displacement curve of this cable. So we have worked with 2 different companies, Fort Wayne as well as Tri-Pyramid, to do testing on these cables independently, to look at the cable in itself and also look at the swage connector. We did have results from the earlier test, but we definitely wanted to validate it for this particular material that we were receiving. And we are happy to note that it kind of matched the shape, the flag shape behavior that we were expecting. And we actually stressed it all the way to 14%, which is basically the strain hardening part. One aspect that differentiates SMA from typical construction material is the temperature effects. While the superelastic behavior still exists at a typical temperature range, there is a minor change that occurs with the yield strength. So when we designed a structure for this, we have to consider the upper bounding properties as well as the lower bounding properties. And then we also had results from durability test, which basically shows that this element does not corrode like steel. There are results from sulfuric acid test as well as separate test and the seawater test, which shows that the steel starts corroding, but the SMA cable still remains intact. And with this, as we said, we have a potential application in here, and Michael is going to go over this because he is our necessity right now.
So, we're super excited that we have a potential application, and even more excited, as Dean Sujay mentioned, that it might be right in the very heart of Berkeley here. We are looking for an opportunity to build on the existing Bechtel Center. Maybe many of you know this. It's a 1980s building, brutalist building. It's sort of half sunk into the landscape. It's maybe not the most welcoming structure or open structure. And so for our student center, we were looking for something that was a little bit brighter. But it does have a robust foundation and a robust structure. So we thought of this as actually using it as a base for our new building. And our strategy is one of load balancing. So through selective demolition of concrete pieces and scraping off the landscaping, we're able to offset that and balance new loads with a lightweight structure that fills in and adds an additional story on top. And this is about saving material, it's about saving money, but it's also about coming up with a more carbon effective solution of reusing existing buildings, and we hope it's a model for other campuses and other buildings for construction. The new building is an open, transparent, outward-looking building with a strong and inviting presence, and it's right on the central campus, right on the central glade. It's also only a few hundred yards away from the Hayward Fault. And the perimeter structure has columns and these diagonal brace systems. And this is our first idea of where we might use the SMA, is on these tension elements along the perimeter. Inside the building, the building is organized around a central top-lit community area that's really we call the forum, and each of the elements of the program and the engineering supports are all around that area, and most of the student-centered spaces are also in that space. And we want to have this we want to have the expression of the structure evident in this Student Center for the Engineering College, and you can start to see the character of it. And I want to just point out the BRB braces that we had proposed on the left-hand side that are sort of part of not just the lateral system, but the character of the interior of the building. And this is sort of the second opportunity we have of using the SMA braces. So we'd like to explore what it means to kind of take those out and replace them with something more like this. So these are a series of lightweight rod and SMA elements. You can see the darker SMA pieces on the end of each of these clusters of 4 tension members. And it becomes, I think, an important part of the way students experience the space, and hopefully provokes them to ask a few questions.